Hello everyone, so today we're going to be looking at chapter 2 of the hazards topic, which is largely to do with the plate tectonics itself, the plate movement and the hazards associated with that. So this is by far the biggest topic, so it's the longest video. We'll work our way through it. There are three sort of key slides we'll be working from, and then I'll go into information for each of the chunks. Pause this at any point you need, and so on and so on, but you do have these knowledge organisers yourselves. So let's start with the basics. Let's go on to the structure of the Earth, okay? And we all are comfortable with the structure of the Earth by the chemical composition, what it's made out of. And that's the crust, mantle, outer core and inner core. So the crust largely made out of granite and basalt. The mantle, silicon and oxygen is the largest sort of elements in that. And then the core itself, the outer and the inner, is both iron and nickel. This used to just be called the core. We only separated this out once they realised how different they were in terms of one being solid and the other being liquid. But in terms of its true chemical composition, it's crust, mantle, core. We have since developed the physical state structure, which is by literally whether it's a solid or liquid, for example. So we have the lithosphere, which is the crust and the top of the mantle. Now, all of this is solid rock, basically. So that's what's called the lithosphere. The asthenosphere is what we know as that kind of gloopy, semi-molten, soft plastic type substance underneath. So that's kind of like from that top part of the mantle that's solid down to kind of the middle part of the mantle. And then we've got the mesosphere, which is the bottom part of the mantle, which is very liquid, would run like water. So that's what's going on there. Now, we've got two types of crust. We've got oceanic crust, which is SEMA, that is silica, magnesium. And then we've got seal, which is silica and aluminium, and that is the continental one. Now, from that then, okay, a couple of things about the mantle. Mantle in general, when we're talking about this, isn't really considered molten apart from that bottom bit, if we were calling it the mesosphere. Now, the reason why rocks melt, why they do become more molten, is because of either an increase in temperature, a decreasing pressure, less pressure on it, or water, okay? So first of all, if you think about magma rising, why is it turning to runny lava when it reaches the surface and comes through the lithosphere? Well, mid-ocean ridges, okay, where the plates are tearing apart. You've got your less dense sort of magma, which is rising, and that melts because of a decrease in pressure, and perhaps an addition of water. Now that's called adiabatic melting. Okay, the temperature of the rock doesn't change. That's what that means. Okay, so that's what's happening at mid-ocean ridges. Subduction zones. Well, the piece that's subducting, that's going downwards, that heats up and it releases water, and it's that addition of water that causes it to melt. And it's very rare for rock to melt due to increasing heat. Okay, that's very rare indeed. That's just a couple of things about that then. So now we come on to plate movement. Now I think convection currents you've been learning about since GCSE, so that's very straightforward. So let's just spend a bit of time on ridge push and slab pull, okay? Basically they think convection currents can't account for all of the movement. So, ridge push then. This happens at mid-ocean ridges, at your constructive plate boundaries. The magma is very warm, it rises, rock is very bad at sort of conducting that heat away. So it causes the rock at that point where it's rising to expand, and that means it's higher up than the surrounding sea floor. That means that basically it's elevated, so gravity can pull it downwards from that ridge to the sort of lower surrounding areas. That's called ridge push, but it should really be called like gravitational sliding instead. It's not very accurate. It's not being pushed at all. It's just being elevated and then gravity is sliding it downwards from that point. So that's ridge push, and that might account for why plates spread apart at our constructive plate margins. At the other end of that then, we've got slab pull. Now, these are at destructive plate margins, and as the plate is going down into the warmer mantle, It's cold. It's the bottom of the ocean floor. So it's denser because it's cold. Now that means it's more likely to sink, and then it basically pulls the plate that it's attached to, the rest of the plate, along with it. So that's called slab pull. And that's considered to be the driving force of plate movement currently. Okay, that's the one that's got the most sort of scientific backing behind it. So that's the structure of the Earth and the plate movements. Let's have a little look at continental drift and plate tectonics. Now this PowerPoint has a lot of information if you need to go back over that on the timeline of exactly how they piece this together. But I'll just sum up some of the key events for you. So back in the 1500s, you had your explorers, Francis Bacon, I don't know how to say that, or Tellius or something, who was Flemish, I think, and him in 1596, he basically was the first person to sort of talk about the jigsaw fit, the fact that he thought that Africa and South America looked like they fitted together when they were mapping the world for the first time. Now, not a lot happened from that until much later on, 1785. The father of geology, James Hutton from Edinburgh, he basically came up with orogenic evidence. He began to note that rock types were formed in different ways and that perhaps they began to match up, so North America and Europe had similar rock types. How could that be accounted for? So orogenic, basically mountain, so we've got mountain evidence coming in at that point. And then 1864, okay, someone called Gervais found the Mesosaurus, the fossil, in South America and in Africa, and we began to piece together the fact that perhaps dinosaurs had been able to walk between places, perhaps they hadn't been far apart, so that was sort of the first fossil evidence. There was also plant evidence as well, plant fossil evidence, but that was kind of the first sort of key date, 1864, for that. And this led to Wegener, Alfred Wegener, in 1912, proposing continental drift theory. The theory that the plates had once been as a supercontinent called Pangaea, and they had drifted into their present-day locations over time. But there was a problem with that. He couldn't explain why or how it happened. So that got thrown out by the scientific community at the time, and it was only when we then had the second half of the story that we began to come together with this theory of plate tectonics by the end of this. So the next piece of the puzzle was Arthur Holmes in 1929. He proposed convection currents, which was the first reason as to why the plates might have moved over time. This was backed up in the 1950s, where we began to do like sub-ocean exploration. Oceanographic vessels started mapping the ocean floor, especially between like here and the United States. So they found mid-ocean ridges for the first time. So that was key, as we could now be like, oh, are the plates perhaps tearing apart at this point? That was kind of the beginning part of that. This was supported in 1960, when seafloor spreading sort of became evidenced. Harry Hess came up with a theory that new crust was forming at those ocean ridges, and the plates were spreading out from there. This was supported just 3 years later by geomagnetic striping, where Vine and Matthews basically figured out that the poles were switching their polarity. North became south and vice versa. I can't remember if it's 500,000 years, I think. But basically the rocks with iron in them, the iron particles were facing different directions. They must have formed at different periods in history. So by the mid-60s then, we began to discover plate boundaries. The Cold War seismographs, they figured out that the plates were moving apart and that we were mapping where the edges of them were. So that's what was going on there, the plate boundaries. They discovered the destructive plate boundaries as well. And this led to the theory of plate tectonics being established in 1968. And I think we overlook who came up with that. That was Dan Mackenzie who came up with that, and he had the evidence to support it by that stage. So there we go. There's the theory of continental drift and plate tectonics summarised. There's a lot more detail for you to go through if you wanted to, and that evidence can be grouped into different categories if you need a structure for that. So we had all of this then. Now we can start to think about the hazards that these particular plate boundaries are giving us. So let's look at the type of lava. It all comes down to the type of lava. This is a key, absolutely crucial. We've got our 3 types of lava. We've got our basaltic lava, our basic lava it's sometimes called, found at constructive plate boundaries largely. We've got our intermediate, our andesitic lava, which is found at destructive plate boundaries. And then we've got our incredibly acidic rhyolitic lava, which tend to focus with the very explosive eruptions. So this table is very handy because it gives you some key information about them. Silica is the percentage of glass, basically, that's what it is, and that literally links up with how viscous, how sticky that magma is going to be. So low silicon content, low viscosity, high silicon content, high viscosity. And the more viscous, sticky it is, means that air bubbles get trapped, pressure builds up, and then you'll have a very explosive eruption. So more silicon, more explosivity. It also gives you some information about how fast that runs. So if it's sticky, it runs slower than if it's running. So think about water, not sticky at all, versus like treacle or golden syrup and how slow that runs comparatively to it. That links into the temperature and the type of materials that will be erupted from that as well. So you tend to get grey style eruptions with your andesitic or rhyolitic, and you tend to get more red style, fissure style eruptions for your basaltic. Also, how frequent they're going to erupt, and the type of volcano and the type of plate boundary they're associated as well. So learn those facts. They're good information to have hold of. So this will lead to different styles of volcanoes. Basaltic lava is more likely to give you fissure style and shield volcanoes. Okay, runny magma, they'll be very wide. These are like the fountains of lava that come out. And then we begin to move to your more andesitic, which is your ash cinder composite dome as well. Caldera tends to be associated with acidic rhyolitic lava as well. So that's by the type of volcano, that's by their shape. We can classify them by the nature of the eruption. I don't like this one so much just because they're more confusing and more difficult to remember in terms of their names. But basically it's like, oh, well, there was a historical volcano and it erupted in this way, so we'll call it that type of eruption. So basic fissure style eruptions, Icelandic, Hawaiian for a shield volcano, and so on and so on. Okay, and as you can see, they're getting more explosive as you move up that scale. So those are your types of volcano. We can now get into the types of hazard associated with this. So here's just a simple table that you can work your own way through. It's from a geofile about all of the different hazards associated with volcanoes and their characteristics and the harmful effects of them. So I'll leave you to sort of pause this and have a look through them yourselves. Definitely worth thinking about which is the most hazardous of them and which is the least. Okay, so try ranking them as a key part of that. Try to think about scale. Are some more dangerous, sort of like in the long term? Are they sort of secondary effects and might have an impact further down the line? Are some more dangerous on an international scale or a local scale? So think about that. Try to bring in scale. That'll help you with longer answers. But I just want to talk about pyroclastic flows very quickly. Okay, fluidized mixture of solid and semi-solid fragments, basically like lava that's cooling down and is becoming solid, and hot expanding gases. And these flow down the flank, the sides, that means, of the volcano. They move like a snow avalanche, except they're boiling hot and not cold, and they are incredibly fast, easily over 100 kilometers an hour. They are the most deadly. Okay, so this is number 1 in that ranking system. And they can be split into 2 types, nuits ardentes or ignigbrites. So the first one then, nuits ardentes. These are basically where there's ash overlying what's going on inside the blocks. It tends to be fine. They don't go as far as ignigbrites, but they are hotter than the other one, and they move a bit faster as well. Ignigbrites then tend to cover a much larger area. They're less compacted, so they're more fluid and basically can reach further as a result of that. Mount St. Helens was an example of that. And then in general, these hazards can be grouped into the gaseous sort of emission style ones, your solid hazards, or your liquids. Okay, so that's what we can do this in. And there is lots of information that you can sort of pick out from the type of lava and the type of hazards there are. So, Pahui is very slow moving lava, and it forms this beautiful like rope-like effect on the surface. Is where it's tearing, it's cooling very quickly. So the bottom's moving faster than the top, and that leads to these blocks on top. You can see Pahoho there, and then there's your on top of it, and it's more spiky. So as you're walking across it, they go as they're walking across. Jumping ahead there. So that's the first slide done. Okay, lots of information there. Beauty of it being a video, so you can go back and check anything, or message me if you've got any questions about this. But let's move on to the next slide then, which is thinking about the actual plates themselves. Okay, this is what catches a lot of people out. What's going on at each of the plates? What are the steps in the formation? So we will start at the beginning. We're going to start with destructive plate margins as a starting point. We're going to think about oceanic. That's what the O and the O mean there. Now these form island arcs. Okay, that's the key thing to remember. They're not island chains. It's not like a hotspot, which we'll come on to later on. These are island arcs, which are called archipelagos. So these are often found on the edge of continents, and they're near the ocean trench. And that trench itself will have differences in the depth of the sea either side of it, because the plate's being kind of twisted like a ruler would if you've got one going underneath the other. One's being bent, and that leads to some sides of the trench being different to the water on the other side of the trench. Now, the next part of that